Let's do some problems involving adding and subtracting vectors at right angles. So we see here that Serena's paddling downstream due south in a boat, I would assume, at a speed of 7 kilometers an hour when she's hit by a gust of wind traveling 4 kilometers an hour due east. What is her resulting velocity down the stream? Okay, so if we draw this out, we have Serena here in her boat. This is Serena, I know, it's a great drawing. And she's traveling downstream south, so we can draw an arrow going down to represent south. We'll call down south. And we know that the length of this arrow is going to be 7. Okay, so this is what's called a vector. So vectors are anything that have a direction and a magnitude. So direction is just the direction that the vector, the thing, the force, or whatever it is pointing. And the magnitude is how long or how powerful, in other words, like the length of that vector is. So if you're traveling at 30 kilometers an hour, the vector to represent this will be much longer. Excuse me. So it's going to be longer than 7. If you're traveling 3 kilometers an hour, the vector to represent that is going to be much smaller than 7. Right? So the magnitude is just kind of like the how big or small the thing is, and the direction is just the direction it's going. Okay, so the vector to represent this is drawn here, and she's hit by a gust of wind traveling 4 kilometers an hour due east. So if we imagine this, the 4 kilometers an hour, that's going to be just over half of the 7. So it's going east to the right, we'll say. And they're asking what's the resulting velocity down the stream? Okay, what's the resulting velocity down the stream? So if we think about this, if we want her final velocity, we can imagine as she's going down and she's getting hit by a gust of wind going east, her boat's kind of going to be offset going down to the right. So if you're traveling straight down and a force pushes you from the left going to the right, you're still gonna move down, but you're gonna be pushed a little bit to the right. So if we want to find out her final velocity, her direction, and her magnitude of her speed, then we're gonna have to add these two together. So this is called adding vectors. So let's take our first vector, which has a length of 7 and a direction going straight down. Right, so this is 7. And let's add it to the other vector that we have right here, which is 4 kilometers an hour going to the right, going east. So when we add vectors, we have to add them tip to tail, it's called. So this is the tip of our first vector, it's where the arrowhead is, and the tail of it is just the other side, it's the back end of the arrow. So this is our tip, and we want to draw the tail of our next vector touching the tip of the previous one. So that's going to the right, that's going to be 4. And we want her resulting velocity. The resultant is just where we start, which was right here, to where we end, which is right here. So these vectors start and end in these two distinct places, and what's called the resultant is just the distance and the direction of the line or the lines connecting these 2 points. So this is the resultant. So the length of this is the magnitude. We can call, like, we usually denote it like this, the magnitude or speed v for velocity, and this is the direction. We can just say theta for our angle. So now that we have this triangle, we don't need this diagram anymore. We're just trying to figure out what the magnitude of our vector v is, and we want to figure out what this theta, this angle, is. So if we want to figure out, first let's figure out the magnitude of her velocity when she's traveling downstream and she gets hit by the gust of wind. So this is a right angle because going south and going east, those two directions are perpendicular to each other. They create a 90-degree angle. So if we remember Pythagoras, a squared plus b squared equals c squared, right? This c squared here, that's going to be the magnitude of our vector v squared. And our other side lengths, our legs of the triangle, are going to be 7 and 4. So 7 squared plus 4 squared is going to be equal to v squared. So 7 squared, that's going to be 49, plus 4 squared, that's going to be 16. That's going to be 49 plus 16, which is 65. Okay, that's going to be the magnitude v squared. And if we just want the magnitude v, remember we square root both sides, so it's going to be 65 square rooted equals our magnitude v. Okay, so if we square root 65, let's get this as a decimal. That's going to be 8.06. So v is going to be 8.06, and this would be in kilometers an hour. Okay, now remember, if we want our velocity, velocity is a vector, speed is not. So if it was asking for her speed, we could just say this. But it's not, it's asking for her velocity. So it's asking for her velocity. That means that we have to find the direction that she goes after she gets hit by the gust of wind. Okay, so after she gets hit, that's going to form this angle theta right here. If we know 4, which is opposite to the angle, and 7, which is adjacent, that means we can use the tangent function. So remember, tangent of an angle is the opposite side over the adjacent side. So tangent of our angle theta, the opposite is 4, and the adjacent is 7. So that means, remember, theta is going to be the inverse tangent of that ratio 4 over 7. Okay, so now if we just go to our calculator here, if we go the inverse tan of 4 over 7, that's going to be 29.7. So we can just say about 30 degrees. So our final answer here, we have the magnitude, we have the direction. So we're going to say that she's traveling 8.06 kilometers an hour, right? And now for the direction, it's going to be 30 degrees, which we just computed. And we can't just say 30 degrees because, like, if someone didn't read the question, they would have no idea what that means. So we have to say, like, 30 degrees where? So if the 7's going south and the 4 is going east, that means that this angle here is 30 degrees east of south. So if this is south, right, 10 degrees east of south would be like just a bit nudged to the right. This would be like 10 degrees. 20 degrees would be kind of nudged a little bit more. 20. 30 degrees would be nudged this much. 30. So the more we nudge to the right, or kind of take this arrow and twist it up to the east direction, the angle theta going east of south is going to increase. So we're going to say 30 degrees east of south, or just E of S. That's a common notation we use. So this is your answer here. Okay, next question here. Ainsley's practicing her running for softball with some of her friends. She sprints to first base, which is 30 meters from the home plate, then straight to second base. Her speed's 5 meters per second, and the distance between home plate, first base, and second base forms a right triangle. How much faster would she have traveled if she ran right over the pitcher's mound from home plate to second base at the same speed? Explain your results. Okay, so before we kind of look at all these crazy words and pieces of information, let's draw this out. So she's on home plate right here. Let me just kind of imagine this baseball diamond. So Ainsley's on home plate. She's practicing running for softball. So if we have first base here, I'll just draw it as a square. And we have, I'll draw it all the same distance here. And we have second base here. They're telling us that the distance from here to here and from here to here, I didn't draw it to scale, actually, I'll draw it a little bit better. They're telling us that from here to here to here is the same distance, and it forms a triangle that is a right triangle. Right? They told us it was a right triangle. So if this forms a right triangle, and we know she's traveling 5 meters per second and the distance to get from home plate to first base is 30 meters. That means that this is going to be 30 meters, and assuming they're the same distance away from first to second as it is from home to first, that's also going to be 30 meters. Okay, so we know that she's traveling 5 meters per second. If she takes this route, how long is it going to take her? The original route, how long is it going to take her to get to second base? Well, we don't have to use Pythagoras for this one because we're not concerned about this distance here yet. We're only concerned about her going from home to first to second, only taking that route. So no weird trigonometry going on here. To find the distance she travels, we just add the distance here to get from home to first and the distance to get from first to second. So her total distance is going to be 60 meters if she takes that original route. So I'll put equals d. That's her distance. Okay, her speed is 5 meters per second, and that's her v. We can call it her speed. It's not her velocity because we don't know exactly her direction at every moment, but we can just say it's v for speed, which is 5 meters per second. Okay, and this question is asking about how much faster would she have traveled, so that's involving time. And we're not sure how long it takes her quite yet to go from home to first to second the conventional kind of way. So if we know the equation here, the velocity is our distance traveled divided by the time it takes, right? That's where we get meters per second because our time is in seconds. Our time is in seconds, and our distance, is in meters. And that's where the two kind of correlate. Velocity in meters per second, that's where the unit comes from. So v is the distance over the time. So that means we can rearrange this a bit and get that time is the distance divided by the velocity. So the distance is 60 meters, and the velocity, or the speed, is 5 meters per second. 60 over 5 is 12, and remember, in this case, our time is going to be in seconds, so 12 seconds. So the way she's running right now, it's going to take her 12 seconds to get from home to second base. So I'll write here in the top left, T1 equals 12 seconds. So that's just the first time that we counted. Okay, and it's asking how much faster would she have traveled if she ran right over the pitcher's mound. So she skips going to first base. She just goes from home to second base. She sprints there. Okay, so if we know that, if I kind of draw this out again, if we know that this is 30 meters, and we know that this is 30 meters, right, and we know that this is a right angle, we can use Pythagoras to figure out the distance from home. This is kind of the pitcher's mound area right here. She runs right over it, and she goes straight to second base. What's this distance? I'll call it d. Well, if this is a right triangle, d is going to be our hypotenuse. So we can use Pythagoras, a squared plus b squared equals c squared. And our legs, 30 and 30, are just going to be a and b. So 30 squared plus 30 squared is going to be c squared. Instead of c squared, I'm going to write d squared. Okay, so 30 squared, that's 3 times 10 times 3 times 10. Now, 3 times 3 is 9. 10 times 10 is 100, so that's 9 times 100. That's going to be 900. So 30 squared is 900. And we have two of them. So we have 900 plus 900 equals d squared. So 1800 is the distance to the pitcher's mound, or sorry, the distance from home plate to the second base squared. Now we have to square root both sides. So the square root of 1800 is d, our distance. And just using our calculator here, that's going to be 42.4. So if she ran straight from home to second base, as opposed to the original 60 meters she had to travel, Now she only has to travel 42.4. So I'm going to erase this part here. If we remember, 42.4 is our distance, right? So we can kind of, I'll draw this triangle a little nicer now. This is 42.4. This was 30. This was 30. This was a 90-degree angle. Okay. So now we can use that T equals D over V formula. So they told us that she was traveling at the same speed, right? At the same speed, except now our distance is different. So now our distance is going to be 42.4 over the 5 meters per second she was traveling before. So if we do that, that's going to be 8.5 seconds. Okay, so that's the time it would take her to travel from home straight to second base. Okay, so now to figure out the difference between them, how much faster she would travel, right? We take our T1, which was 12 seconds, and we subtract it. So I'll write T difference, or just T diff, equals our first time minus our second time. So our first time was 12 seconds, minus our second time, which was 8.5 seconds. And it's going to be 3.5 seconds. So if she travels straight from home to second base without going to first base, she's going to get to second base 3.5 seconds faster. Next question, draw the resultant vector when these two vectors are added and subtracted. Okay, so this notation here, F with a little arrow on top and same with G, that just means it's a vector. And the components of these vectors, the things, the direction that makes it up, the magnitudes, are 6, 0, 0, and 3. So the top number in this type of notation, this is the horizontal direction, or just the x direction. The bottom number is the y direction. So if we look at V here, it's going to go 6 in the horizontal direction, so 6 to the right, and 0 up or down. So it's not going to go up or down like this because the vertical component is just 0. So this is our F. Our G, on the other hand, its x component is 0, and its y component is 3, positive 3, so that means it's going to go up. So it's going to be half the magnitude as the x component of F, except now it has a vertical component instead of horizontal. So let's say we take these two vectors and add them. That means that we're taking F and we're drawing it tip to tail, remember. So we're drawing the tail of G touching the tip of F. So this is going to be a length of 6 and a length of 3. Draw the resultant vector. It doesn't want us to compute the actual value, just draw it out. So remember, the resultant vector is where we start to where we end. So that would be this one right here. Okay, that would be the resultant vector if we added them. Now if we subtracted them, remember, if we have like two numbers a minus b, this is the same as a plus negative b. So if we just added two vectors, f plus g, that was pretty easy because we knew what f was, we knew what g was. If we added them, we could just add their components and draw it out. Now f minus g is the same as f plus negative g. Now negative g is the same as g, except it's working in the opposite direction. Okay, it's working in the opposite direction, so it's going to be going down now instead of up. So underneath here, I'll write f plus g, and these little arrows on top just mean they're vectors. Okay, now f minus g, that's going to be the same f. That's going to be the same f, except, so this is 6, except now it's negative g. We're adding negative g. So it's going to be going down by 3. So I'll draw it right there. And now the resultant vector you'll see is going to be going right here. And this is always where we start to where we finish. We have our arrow here. And once again, we don't quite need to compute it. And whether we add, so like for this example, this was f minus g. And if it was g minus f, right, you can imagine we get a different result. So if we had g, right, if we had g going up, and we're subtracting f, that means that we're going in the other direction now. So we're going 6, we gotta draw tip to tail though, so we go 6 to the left, and then the resultant vector is here. So it's parallel to the vector we just did, f minus g, except it's working in the opposite direction. It's working bottom right to top left now, instead of top left to bottom right. So those are kind of the similarities there. Okay, last question here. The vector h has components 5 and 8. P has components -1 and 9. Let's figure out h plus p and h minus p. So one way we could do it is draw out a vector h with a horizontal component of 5 and a vertical component of 8. We could get that resulting vector. Okay, so this here is just h, this resultant vector with the two lines. This is h. And p is -1 and then up 9. So it's going to be -1, up 9. So it's going to be a super steep vector. Actually, I'm not even going to write the distances there. And then the resultant is going to be where we start to where we finish all the time. Oops. It's going to be right there, where we start to where we finish. Right? So this is going to be p. If we're adding them, we're just taking the two resultant vectors and adding them together like we did in the last problem. And we could use like what's called the sine and cosine law to figure that out. But the easiest way to do it, okay, is forget all this. And we can just look at which direction the components are acting. So if we're adding h and p, we're really adding the x components together, and we're adding the y components together. So the new components of this vector are going to be 5 plus -1, and then the y components are going to be 8 plus 9. So we're just adding the two components together from each respective vector. And 5 plus -1 is 4. So this is going to be 4, and 8 plus 9 is 17. So we're going to draw a vector with a horizontal direction or length of 4 and a vertical magnitude of direction length of 17. And we could use Pythagoras to calculate the angle and the magnitude, but you get the idea. So this is going to be your angle. So it's going to be north of east, and you can just call this length h arrow plus p arrow. So these are the two vectors being added. If we're subtracting them, you can imagine we're just subtracting the x and y components of p from the x and y components of h. So 5 minus -1 is going to be 5 plus 1. So the components of this would be 5 plus 1, which is 6, and then 8 minus 9, which is -1. So the 6 represents the x, -1 is the y. So it's going to be 6 in the x direction, and then -1 in the y direction. -1, right, 6. We started here, ended here. So we're going to draw a resultant vector right here. And this is the vector that you get when you subtract them, specifically in the order h minus p. And you could switch the order. It would still be parallel. It would just be going from the bottom right to the top left now. Okay, so that's kind of an introduction into vectors and how we can use trigonometry to solve problems like these. I hope it was helpful. And yeah, this is kind of building a good foundation into your knowledge of trigonometry and vectors, right? Anything with direction and magnitude. So drop a comment if you have questions, and if you want your name to be in any of these examples, just message me and I'll make it happen, all right? I'll see you guys later.